Oh, yeah, that's free.
106. This is a great lecture because it pulls a whole bunch of things together. Translate the code. When the professor says this is a great lecture because it pulls a whole bunch of stuff together, what does that mean? Ben says it means you're going to be confused. It also just means that when you focus hard, you could see a lot of things come together. It isn't a lecture that you can sit back and casually let it wash over you.
That's not good.
Actually, are there any of our 106 lectures that are that kind of lecture? No. Okay. Let's start with a prayer. We have a volunteer to pray for us. We always need it, right? Particularly before. Josh, you want to do it from the back?
Our Father, which is in heaven, we ask thee at this time as we seek to learn this material that we might have our minds open and that we might be enlightened. Father, we pray that in this time that can be a little bit more stressful than other times of the year, we might be able to see you with us to comfort us, and that we might keep in mind our purposes as thy children. And Father, we pray for these things and ask you this in the name of Jesus Christ. Amen.
I'd like to point out, all of you are highly committed, highly focused, highly stressed BYU students. Got there? I would just like to remind you that you are not going to stand at the judgment in front of the Savior, and the Savior is not going to say to you, so what was your GPA fall of 2021? Right? So, if possible, I would like you to shift from a perspective of doing everything you can do to be successful and being tied in knots about it, to doing everything you can do to be successful and trust that whatever life plan you have in front of you, the Lord can help it happen. Because you're going to do the best you can do anyway, right? I want to tell you that from my personal experience in my life, the Lord has opened doors for me to do what I needed to do. I don't think that I'm special. So I felt like the Lord was asking me to make a specific contribution to go into science. And I worried about how would I juggle that with my family and how would I be successful. And I was a student that did have to work harder than other students for the same GPA. And I had an experience during my sophomore year where the Lord told me not to worry about it, that it would be okay. And my response to things like that is to say, okay, message heard. And then I have a hard time not worrying. It's a little silly, right? I want you to know that the Lord meant that promise, and things have been smoothed, and there has been a way for me to serve and to continue to do science. Okay, what does that mean for you? What that means for you is it's not all on you. And if the Lord is asking you to go to medical school or to serve in a certain way or to go to PA school or to do a certain thing, if that's required of you, if it's a specific way that the Lord wants you to serve, then you go ahead and do your best. The Lord will help it to happen. And if it doesn't happen, that means that the Lord values all different kinds of service and that you can live a valuable and successful life not going to medical school, that the Lord will use wherever you are to serve. So what I'm telling you is, of course you're going to work hard and of course you're going to focus, but the stakes are not as high as they feel. You guys are at a place in your life where you feel like what you do now, you're going to make or break everything. And that's not really how it works. There's more than one way to do things. And if it's something the Lord asks you to do, the way will be made clear and it will happen. So if possible, I would like you to pull up your reserve of faith, take that anxiety and that worry and that angst, and in prayer, hand it back to the Lord and say to the Lord, I trust you to make the things happen that need to happen. And then just give that up. You don't have emotional energy to spend on worrying about those things. Because you just don't, right? That's my request for you today. I understand that it's not as easy as flipping a switch, right? But if as part of your prayer, you could ask the Lord to help you not be afraid, to trust him. And you can say a prayer. I've said this prayer before. I said it when it was, my husband and I got the prompting that he should be applying for an opening position at BYU. And my daughter was finishing her junior year of high school and really did not want to move. My mom needed triple bypass surgery and I needed to spend the summer with her, and I couldn't spend the summer selling our house and moving. My sister was having twins and I needed to be in Alberta, not just with my mom, but to help my sister who eventually delivered a 7 and an 8 pound baby. So her mobility was a little low. And then I felt like the Lord wanted us to go to BYU, and those things were not compatible, right? So I prayed the prayer that said, Heavenly Father, I know that all these things matter to you. I know you love my daughter and her experience. And she was having nightmares about driving away from Clemson. I know you care about my mom and my dad and what they're battling with this surgery. I know you care about my sister and her twins. I know you care about BYU. I know you care about my husband and I have no idea how this can work. So please just make it work. What happened? A miracle happened. The miracle was that my husband got offered the job. Normally you get offered the job in the spring and they expect you to be there at the end of August to start the semester, right? And when the department chair came to him, he said, yeah, we don't usually do this, but actually, we don't actually care when you arrive. So you could come in August, or you could come in January, or you could come next May. And my husband said, well, I have a daughter that would really love to finish high school before we move, so we'll come next May. Was that an accident? No, because when you go to the Lord and you say, there's a way to make this work, only you know how to make it work. Please take care of it. And you hand that worry back to the Lord as an act of faith, and miracles happen. So consider you have the privilege of asking for miracles, that you can say, if this is meant to be, and I need to do this certain path, help me to know how to make it work. And then trust that whatever the outcome, it will be okay then. Anyway, I don't know whether you wanted to hear that from me, but I haven't forgotten what it feels like to be where you are. Yeah, I still remember. Okay, let's talk about actual chemistry stuff. Couple things. You are all deeply and physically aware that the exam starts on Friday, right? It runs through Tuesday. It covers lectures, what? 5, 6, 7, and 8. Okay. 24 multiple choice questions, 4 pages for answer. Keep in mind that the solubility that we're doing today is kind of the capstone. So take the concepts that you used the previous 3 lectures and apply them to solubility. So there may be slightly more solubility questions, not because that's different material, but because that is an easy way to apply what you know. Okay. There is a mock exam, as always. It's due Monday at noon. That's the last possible moment I can make it due and still have you show up and get feedback from the office hours. I am gonna do an extra Zoom office hour tomorrow. 3:30. So best possible scenario, you do the mock exam before then, so you can come and talk to me about it. That's fine if you don't get to that and you just have your other list of questions you want to ask me. Okay, check the recitation keys. How many of you have had the experience of you do the recitation the first time and you think you have it completely mastered, and then before several weeks in, you open up the recitation again and it's like they're different questions? That, or you read the key and you thought that you understood what the key said before, but then you come back to it and you're like, whoa, there's a whole bunch more stuff here, right? So go over the recitations in advance of that. Many of you have noticed that up to now, the Salt Lake Center hours for testing were paltry, right? What had actually happened is that they were short-staffed and so they couldn't offer 3 hours. That problem has been solved. So there are now extended hours for those exams. Students who travel to the Salt Lake Center to take the exam actually really like it. Okay, let's talk. With your neighbor, handful of equations that summarize all the ideas in the course, all the thermodynamic ideas. This is one of the important equations. Is this the only version of this equation? What does the other version look like? Delta G naught. Yeah, you can express it as minus RT natural log of the equilibrium constant. How come you could do that? Delta G naught is minus RT natural log. Okay, tell your neighbor what delta G is. Sorry, delta G naught. Delta G naught is the delta G value measured, the value of delta G measured under a specific set of concentration conditions, which are 1 mole per liter or 1 atmosphere of all starting materials and products. Why would we choose those conditions? If I write a rice table for that, what does it look like? One on both sides, right? Equal amounts of starting material and products. Okay, if the equilibrium lies to the left, which way will that reaction go from that set of conditions? Let's draw. I have to change. Wrong way for it. Okay. So if I have a reaction, we're going to make it as easy as possible. A goes to B, right? If I'm running the reaction under standard conditions, like that, right? Okay. From this position, if delta G naught is negative, what will happen? Delta G naught is negative. Under these conditions, negative delta G naught means the reaction is going to move towards products, right? Then where will the equilibrium lie? Lie to the right. We'll end up with more product than starting materials. Okay. Now suppose that for a react, but instead of delta G naught being negative, delta G naught is positive. What does that tell us? Where will the reaction run? To the left, so where will equilibrium be? To the left, so we'll end up with more starting materials and products, right? So what delta G naught actually tells us is from these conditions, where will the equilibrium lie? What else tells us that same information? K value does, right? K tells us where the equilibrium lie. Okay, are we back to every time I touch the screen, it stops responding. Josh.
So delta G is just the difference in potential energy of the atoms, like minus whatever gets lost to heat or entropy or enthalpy, sorry.
It's delta G naught represents what the difference in entropy would be totally from that to equilibrium.
Okay.
So all those deltas is difference, right? So what we're comparing is the difference between where we start and where we end up. And where do we always end up? Equilibrium, right? So this delta G naught value tells us, starting from 1 molar starting materials and products, what's the change in the total free energy from there to equilibrium? Okay. At equilibrium, let's take this equation. At equilibrium, Q value equals the K value. Delta G equals 0. Delta G naught equals 12. Okay. Conditions here where everything is 1 molar. What's the Q value? It has to be 1, right? If all the concentrations are 1, Q is 1. If Q is 1, what's the value of this second term? If you take the natural log of 1, you get 0. So under those conditions, delta G equals delta G naught. Okay. So what's delta G? The delta G naught is which way the reaction wants to go, starting from equal amounts of starting materials and products. So what's delta G? Do we have any possible rate of concentrations that we could start from? Delta G is just the delta G value starting from that position, whatever it is, and the difference between that and equilibrium position. Okay. So delta G naught tells us from the standard position, 1 molar of everything, how much does the universe want to push the reaction forward or not? And delta G is how much does the universe want to push the reaction forward starting from any other set of concentrations? Okay.
Backward.
Yes.
Does that mean that delta G serves kind of the same function as Q as well?
Q tells us where we are on a way to equilibrium, right? So does delta G. Yeah. In fact, they're related because delta G, for a given reaction, has a set value of the equilibrium constant, right? So the Q value determines whether delta G is positive or negative. So delta G and Q are linked conceptually. K is linked to delta G naught. Okay, because K and delta G naught tell you where the equilibrium will lie once you get there, right? And Q and delta G tell you what side of the equilibrium are you at. When Q is less than K, what side of equilibrium are we on? We're still to the left of equilibrium. So the reaction is going to move forward in order to get to equilibrium. So delta G is negative. Okay, if Q is greater than K, where are we relative to the equilibrium position? We have too much product. We're past equilibrium. So the reaction is going to have to move backwards to reach equilibrium. So then delta G is positive. Can I say that again? K and delta G naught both tell you what equilibrium will look like. Is it going to lie to the left or the right? How far to the left or right it's going to lie, right? Q and delta G both tell you where you are at that moment relative to the equilibrium position. Are you not to equilibrium yet? Are you past equilibrium? And once we have those things, if we know where equilibrium is supposed to be, and we know where we are relative to equilibrium and the conditions that we have, do we know everything we need to know to track the progress of a reaction? Yeah, we do. Okay. So every reaction is going to start where it is in terms of concentration and proceed towards equilibrium, right? So functionally, what happens for every reaction is as the reaction proceeds, Q gets closer and closer to K, right? So Q reflects the concentrations. It comes from the concentrations. So as your concentrations change over the course of the reaction, your Q is going to change and get closer and closer to K. What happens to delta G then? It gets closer and closer to 0. Absolutely. Okay. So if we have this equation, we can read from the math. As Q gets closer to K, delta G gets closer to 0. Okay. Okay. Does delta G not change as the reaction proceeds, as Q gets closer to K. How can you tell conceptually? How can you tell mathematically?
Conceptually, delta G naught is the whole entire reaction under standard conditions from start to beginning, what you would expect.
So that's the delta G naught is the value of delta G if the concentrations were standard, right? As a reaction proceeds, can that value change? That can't. Delta G naught is a reference value. So it's a constant for a given reaction with a specific K value at a specific temperature. It's what we use to compare reactions. So delta G naught doesn't change as the reaction proceeds. Does delta G change? Yes, it does. Yeah. So delta G naught is a reference point, but it's a reference point that we've chosen to make it conceptually easy to think about where equilibrium will lie. Okay. There is one single image that illustrates the connection between the K value and the Q value and the delta G value. This is it. One of the things that's confusing about these plots is the y-axis is always Gibbs free energy G. Notice, is it delta G? Just G. Okay, but it's delta G that we care about, right? So what on the plot of G is delta G? Slope, okay? So all of these plots have G as your y-axis. But then, just because chemists like to confuse students, apparently, they label the x-axis a whole bunch of different ways. One is to label it extent of reaction. From 0 to then what would this be over here? It'd be 100%. So what does that mean? 0% reaction would mean what? All starting material. And what would 100% reaction be? All product. Okay. Sometimes instead of extent of reaction, it's labeled percent composition. In which case, what would this be? 100% starting material. What would this be? 100% product. What would halfway in between be? 50% starting material, 50% product. Okay. This is actually a manifestation in some ways of this equation. So we can read the delta G off the slope. How do we get Q and K off of this plot? So we know that at equilibrium, delta G is 0, right? And equilibrium occurs for every reaction at a specific amount of starting material and product, right? Can we read that off this plot? Where's the slope 0? Right here, right? Okay. So does that tell us something about the position of equilibrium? Delta G, the slope is 0. We read down approximately what percentage of starting material and product is that? About 50%, right? 50% starting material, 50% product. What value of K correspond to? 1. So this is a plot that approximately shows how delta G changes as a function of changes in concentration if the K value is 1. Okay. If K is here, does that mean that at this point on the plot, Q equals K? Yeah, okay, so if we get more starting material, then Q equals K. What do we know about this whole part of the plot to the left of equilibrium? Q is less than K. Okay, when Q is less than K, what's the sign of delta G? It's negative. Can we see that on the plot? So whatever different amount of starting material and product we start with, every time Q is less than K, where does the reaction want to go? To go forward to reach equilibrium, the slope is negative, delta G is negative. Okay. How about this part of the plot? all of these percentage compositions are past equilibrium, right? We have too much product. So what's the Q value? Right hand side of the plot. Q value is greater than the K value. So if we're moving forward, what would the delta G be? Positive. So if you start at any of these percentage compositions, which way is the reaction going to go? Drop a marble, it's going to fall down to equilibrium, right? And stay there. If we start a reaction at any of these percent compositions, the reaction will move backwards, get to equilibrium and stay there. Does this plot represent a single reaction? No, it doesn't. It represents what the delta G value would be at every possible value of Q. That's what it represents. If we were looking at a single reaction, how would we interpret this plot for a single reaction? We have to start a single reaction at a certain set of concentrations, right? If we start the reaction with all starting materials, where are we on the plot? We start right up here, right? Okay, and the reaction is going to move forward. As the reaction moves forward, we're producing more product by using up starting material. So our extent of reaction is going to change, right? So the reaction moves forward. What happens to the value of delta G? It gets closer to 0, and it starts more negative because the plot is steeper. And as the percentage of starting material changes, the delta G value becomes less and less negative. So the farther away we are from equilibrium, the farther the delta G value is from 0. Okay. Connect that. So a single reaction doesn't move through all those concentrations, right? A single reaction starts whatever composition you start with. Plot of delta G versus time. What would it look like? Where does it end up? It ends up at 0. So you draw a 0 line here. Let me change my camera. Okay, so if we're drawing delta G versus time for a reaction, for a reaction proceeding forward, every reaction is going to move towards equilibrium, right? In equilibrium, delta G is 0. Once the reaction gets to equilibrium, is it going to stay there? How long will it stay there? Forever, unless you change something, right? So we're going to end up at 0. Start with Q less than K. What's our value for delta G? Negative. As the reaction proceeds, it's going to get less and less negative. Curve. So this is for the forward reaction. For the backwards reaction, what would our delta G be?
Starts positive.
Start positive, but it's actually going to move backwards, right? So for the backwards reaction, the delta G is positive. As we move backwards, Q gets closer and closer to K. And those curves should be mirror images of each other. I don't know that I've drawn them perfectly. Okay, how about G versus time? Can we do that? Where will the reaction end up eventually? At equilibrium, right? At equilibrium, delta G is 0. What's G? Do we even care? We care about delta G. How would we show delta G equals 0 on a plot of G? The slope. So when we get to equilibrium, the slope is going to be 0, right? Okay. We're starting from Q less than K. Suppose we start with all starting materials. What's the plot going to look like? Slope has to be negative because the slope is delta G. So we're going to do something like this. Like that. Yes. Okay. Let's go back to the screen. Okay. One thing to keep in mind is if you change the temperature. That's if I don't have that on the screen, right? If you change the temperature, you're gonna change K, and you're gonna change delta G naught. Why does K change when you change the temperature? But what we're saying is the position of equilibrium changes. By changing the temperature, you can change whether you get more product or less product. How come? It's not a trivial question, right? Josh.
Here's the forward versus the reverse reaction rate.
Yes, it has to do with the forward and reverse rate constants. Okay, so we know that the actual equilibrium constant theoretically comes from the ratio of the rate constant for the forward reaction and the rate constant for the backwards reaction. We also know that the rate constants come from e to the minus EA over RT, which means for a given temperature, does the energy of activation change with the temperature? Energy of activation is set by the structure of the molecules themselves as they move from starting material to product. So that doesn't change with temperature. So the energy of activation is set, it's a constant. If you change the temperature, then the whole K value is going to change, right? But do you typically have the same energy of activation for the forwards and backwards reaction? You don't, right? Which means that your rate constants for forwards and backwards are going to change to different amounts when you change the temperature. So then the ratio is going to change. So then the equilibrium constant is going to change. Okay, so K has to change with temperature. Why does delta G naught also change with temperature? There's about 4 different ways to answer this. One is to say your K value, your equilibrium constant, tells you where equilibrium is going to end up at, right? And if the K value changes with temperature, then that has to change everything else that tells you where equilibrium is going to end up. And what does delta G naught tell you? It tells you kind of where the equilibrium is going to end up. So if one changes, the other one has to change. Another way to look at it is to say, well, mathematically, duh, they're mathematical transformations of each other. So if you change the equilibrium constant by changing the temperature, well, you know that delta G naught. It also has to change because you can't change K without also changing delta G naught. Okay, the other way to look at it is to use this expression, delta G naught equals delta H naught minus T delta S naught. Okay, just from that equation, if you change the temperature, what happens to delta G naught? It changes. What delta H naught and delta S naught, do they change with temperature? They don't. Just like the energy of activation, delta H naught and delta S naught actually come from the structure of the molecules. So it comes from the strength of the bonds, it comes from orbital overlap, all the sort of things that you don't remember from Chem 105, but remember not liking. All of those things from Unit 2 of Chem 105, those things influence delta S naught and delta H naught, also Unit 3. Okay, so because this is Chem 106, we don't ever have a conceptual relationship that isn't also stated in an equation, right? This is physical chemistry, and every important concept in physical chemistry has a translation in an equation. So what is the equation that tells us the relationship between the temperature and the K value? So you could actually calculate it and predict it. It's one of the few named equations that we have. Okay, step back for a minute. Claim your birthright as a physical chemist, right? You're in a physical chemistry class, you're learning physical chemistry. So say to yourself, I am a physical chemist.
I am a physical chemist.
Okay, you may feel like a novice physical chemist, but you're a physical chemist. And as a physical chemist, when you have a question, you want to answer it with an equation, right? So we want an equation that has K on the the left-hand side, and temperature on the other side, because then we'll have an equation that tells us how does K change with temperature, right? So you have these two equations that you can work with. So let's assume you're doing a physical chemistry thing and you just start messing around with equations, right? What can you do with those two equations? You can set them equal to each other, right? So set them equal to each other and then you get this equation. Can we rearrange this equation in such a way that we put the temperature on one side and leave K on the other? Yeah, so we do a little bit of rearranging and simplify, and we end up with the Van Hoff equation. The Van Hoff equation is just a rearrangement of setting these two things equal to each other, so that we have K on one side and temperature on the other. Because that's what physical chemists do when they want to know how much does K change with temperature. Well, you come up with an equation. You always put the thing that you're interested in on the left-hand side. And if you want to see how it changes, you put that thing on the other side. So that's just what we did. Okay, so what does that equation tell us? It tells us, first of all, that K does change with temperature, right? We already knew. But it tells us that the amount of how much K changes with temperature depends on the delta H naught value. Okay, this is delta H naught value. What does that have to do with the energy diagram? Yeah, it's the enthalpy value. It tells you whether it's an endothermic or an exothermic reaction. Okay. One thing to keep in mind about this equation, does delta H not change with temperature? No, it doesn't. Does delta S not change with temperature? Not much. So we assume it doesn't change at all. You may remember from Chem 105 that, how do we calculate the S naught values? Does anyone remember from Chem 105?
Stone equation, right? The one that.
Yeah, the tombstone equation that has the sigma on it. You sum up the standard molar entropies of the products as a function of how many moles there are of each of those things and subtract the sum of the standard molar entropies of the reactants. And you get a delta S naught from that value. Well, the S naught values, the standard molar entropies, do change slightly with temperature. But when we're looking at chemical reactions over the course of the over the temperature ranges that we typically look at, it doesn't change enough to worry about.
Why don't exothermic reactions like for their equilibrium further? Because they raise the temperature of the solution that they're in, right? And then the temperature that they produce.
Yes, and we pretend that doesn't happen when we analyze these, right? And mostly it doesn't happen because those reactions, you're actually giving the heat out to the surrounding environment. To make this strictly true, you'd have to set things up in the reactions in ways that kind of suck the extra heat and kept it at constant temperature, right? Okay, so we have this equation, that Hoff plot. Other thing that physical chemists always do, if they have an equation, they plot data according to that equation, right? So how would we put these plots on? Can we measure equilibrium constants at a bunch of different temperatures? How would we do that? Measure equilibrium. Set up a reaction, let it come to equilibrium, measure your final equilibrium concentrations of everything, plug those back into your equilibrium constant expression, and then you'll get K. So you do that for a whole bunch of temperatures. I've done that. And then you plot, take the natural log of the resulting equilibrium constant, plot it over 1/T. And then you get a plot that you fit with a line. What does the line have to do with the equation? Say louder.
Y equals mx plus b.
Yeah, this is the equation of the line. It's expressed in the terms of y equals mx plus b. Natural log of k is your y. That's why it's on your y-axis. 1/temperature is your x. That's why it's on the x-axis. Okay, so what's the slope then? The slope is minus delta H naught over R. Why does that negative sign matter? Well, it has to be there because it came out of your math, right? But in terms of translating the plot, this negative sign means The sign of delta H is always opposite what the slope is. If you have a negative slope, what's your sign of delta H? Positive. So a negative slope on a Van Hoff plot corresponds to positive delta H or an endothermic reaction. If you have a positive slope, that corresponds to what? Negative delta H naught value or an exothermic reaction. Okay. If you know that, it can draw the plot. It can help you keep straight what happens to K as the temperature goes up. Okay. We're plotting 1 over temperature, right? So where on the plot are the higher temperatures and where on the plot are the lower temperatures? So when your temperature goes up, what happens to 1 over T?
It's small.
It gets smaller. So here are your highest temperatures. As we move from left to right on the x-axis, what's actually happened to the temperature? Decrease. Okay. So if we want to say what's happening to our K value as the temperature goes up, we have to move from right to left. So as our temperature goes up, what happens to K here? Increasing. Okay. So here we have positive delta H naught on the equation corresponding to an endothermic reaction. So for an endothermic reaction, as you raise the temperature, what happens to your K value? What's up? Can you do the same thing but also exothermic reaction? Yeah, you can. Okay, we do have one more form of the equation that we use. Measuring equilibrium constants takes time and materials and manpower. So if you can come up with an indicator of the delta H naught value, for example, and only have to measure 2 equilibrium constants at 2 different temperatures, does that have some advantages? Sure. So in order to make this 2-point form of the Van Hoff equation, we take an approach that's very similar to what we did in Unit 1 when we were talking about the 2-point form of the Arrhenius equation. Take the Van Hoff equation at 1 temperature, which will have 1 value of K, right? And you take the Van Hoff equation at another temperature, which will have another value of K. Subtract those equations from each other, then what happens to this delta S naught over R? Delta S naught doesn't change with temperature, then what happens to these two terms? You subtract out, right? So what you're left with is an equation that only has delta H naught in it and not delta S naught in it. And then you can simplify it. Does this Van Hoff equation have the same mathematical permutations as the 2-point form of the Arrhenius equation? And it doesn't have a delta, it doesn't have a negative. Usually it's presented. Flip your K2 and T1, negative sign goes here. You flip your T2 and T1. But be very careful when you're actually doing problems like this, say for example on an exam, that you put your numbers in the right place and you don't leave out the negative sign. What's the other thing you have to keep in mind? What units do you have to use for delta H naught? Joules. And delta H naught values are often reported in kilojoules. So make sure that if you're reading a value that says what the delta H naught value is in kilojoules, that's not wrong. Put it into the equation. What do you have to do? You have to convert it to joules. Otherwise, off by 1,000-fold. Values are going to be off. Okay. And we did that problem, recitation problem, in recitation 7. You take the equation. It asks you to solve for the delta H naught, so you have to rearrange the equation. Plug your numbers in. Get the right number. Okay. So classic blenders. Yes.
I was just wondering, this equation is not on the equation sheet. Do we need to memorize it?
It's actually on the equation sheet on the exam. So did it not make it onto the one?
It's not on this one.
Having trouble formatting that last equation, you kept flipping from side to side. It just ended up disappearing. is something that will show up on the equation for the exam. You want to write it on your sheet that you're studying from. Thank you, Ally. I didn't realize that. Okay, so there are actually 3 classic blunders in using this equation. One is to take the delta H naught value, if you're given that, and make sure you express it in joules. It's common for people to put their numbers in the wrong place. You're putting 4 different numbers in 4 different places, right? So double check that you're doing that correctly. The other classic blunder is Celsius instead of Kelvin. Is there any place in Chem 106 where you use Celsius? You can't. Thermodynamic equations come from theoretical statistical mechanics derivations. Assume related to entropy. Standard molar entropy changes eventually with temperature. We don't ever use Celsius in 106. In fact, you actually don't ever use Celsius in 105 either, except when you're using a difference in temperature. How can you use Celsius in 105 for that application? Because the change in temperature in Celsius is the same as the change in temperature in Kelvin. So actually in Chem 105, you should have been using Kelvin too. It's just that the change in temperature is the same, so we didn't. Okay. Over this one. So, quick, tell your neighbor. 4 things.
That's delta. What if it's?
Yeah, it tells me.
Yeah.
It tells us where you're at. It does. It does too.
Delta G.
Yeah, so and it does too. Get away with that is.
Delta H naught and delta S naught. Those come from the structure of the molecules themselves. Essentially, delta H naught comes from the energy diagram. Position of starting material and products. Delta S naught comes from the difference in entropy between the molecules of products and starting materials. When there's a knot on there, what does that mean for that? Does it mean it has to be at a specific concentration? In Chem 105, when you calculated delta H naught for a reaction, how many moles did you have? Delta H naught typically is expressed in units of kilojoules per mole. The delta H naught is for 1 mole of the total material. Okay. That's not.
So I don't want to interrupt, but like, so with delta H naught, if you change the concentrations, wouldn't it just like lower, like, would the difference be the same always? That
The difference per mole is the same.
the difference per moles?
So if you run 5 moles, total heat output is going to be 5 times as great. Right?
Right.
So that the H naught value is a reference value. So we have to assign how much material we're talking about. We're talking about 1 mole. We'll track our delta G naught, delta G. A couple of kinds of K values we've seen so far, right? What are KC and KP? Those are equilibrium concentrations calculated, or equilibrium constants. KC is calculated by measuring the molar concentration of product and get an equilibrium. KP it only applies to gas phase. And what you do is you run a reaction in the gas phase and you measure the partial pressures of products instead of molar concentration. Partial pressure is just a different way to assess concentration. But you get the same number when you calculate the K with partial pressure that you do calculating K with molar concentrations. No. So we call them differently. Now, in most of what we've talked about, we just call each of them an equilibrium constant. They aren't necessarily the same thing. Okay, Ka, what's that? We briefly mentioned when we introduced K values that there's a kind of equilibrium constant that gets applied to a specific kind of acid-base reaction. That's Ka value. By the end of unit 3, even Ka values will be like this. Okay, last time we also introduced a Kf value. Anybody remember what that is? Okay, it's called a formation constant, and it applies to a kind of process called metal chelation, where you take a metal cation with empty orbitals, and it forms a reaction with something that has lone pairs that can go into those orbitals. Okay, today we're going to do a new one, KSP. And KSP is fabulous because it's the easiest math of any equilibrium calculations that you will ever do. Good for me, woohoo! I'm happy about that, right? Okay, first thing to keep in mind, KSP values typically apply to the process of dissolving. So, now, strictly speaking, is this a chemical reaction? Isn't exactly a chemical reaction. However, all the concepts of equilibrium still apply to it. Okay. So if we take an ionic solid, remember ionic solids are typically, they are composed of a cation and an anion that are held together by charge-charge attraction. Okay. If you put an ionic solid in water, those ions can actually come apart and float freely in the water. How come they can do that? So what holds them together into the ionic solid? It's an attraction between positive and negative, right? So if they come apart, there has to be something that's compensating for that charge-charge force, right? Tell me about water as a solvent. It's highly polar, right? Meaning that water has a partial positive and a partial negative charge on it. And what actually happens when the ions come apart and dissolve and float, each negative ion is going to be surrounded by a whole cluster of water molecules that have their positive end pointing towards the ion. So you're still having some kind of charge-charge interaction because there's a whole bunch of water molecules, kind of the sum of all of their partial charges can actually create a stronger interaction with the ions than you would see in salt. Okay, for the positive ion, what end of the water molecule is going to be closest clustered around the positive ion? The oxygen end, which is negative. Yeah, so that's what happens when things dissolve. Okay. When we draw the so terminology here, dissolving, we call that the process of solution. When you're forming a solution, process of dissolving, we call that a dissolution process. As in to dissolve, it's called dissolution. Okay. So we write out the process of dissolving as if it were a chemical reaction. So for example, sodium fluoride, that's an ionic compound, positive sodium, negative fluoride ion. When it dissolves, those ions come apart. We specify that those are aqueous, meaning they're dissolved. Okay. For magnesium chloride, when they come apart, how many chloride ions do you have per magnesium ion? There's 2 chlorides. So when you do the dissolution equation, geometry of 2 in front of the chloride. Okay. When we do an equilibrium constant for this, the equilibrium constant is going to be the concentration of the products. What do you know about the starting materials? They're solids, so do we include them in the equilibrium expression? No. So the equilibrium constants are just the product of the dissolved ions raised to whatever the power of the stoichiometry is. Okay, so why is this called a KSP value? What does SP stand for?
Solubility product.
It stands for solubility product. Why do we use the word product?
It's multiple step.
It's a multiplication. So math language, a product of something is multiplied. Normally our K values would be a quotient, right? Because you're dividing by something. But when we do solubility, there's nothing in the denominator except 1. So it's a product instead of a quotient. So we call it a solubility product. Okay, what does that do to all your rice table calculations? It makes them so much easier. Yeah. In fact, some of these you can do in your head. If we're dealing with equilibrium constants, does that mean that all of the concepts and equations that you've learned up till now just apply to this? Yes. Nothing new here, but easier math and some new vocabulary. Okay, so reading quiz feedback question. How does K differ from KC and KP? Answer is it's the same idea, but easier math. So really, it's not different at all, except how we define it. Okay, there are some new vocabulary that you need to know, which is frustrating, right? But this is how the history of chemistry worked. All these branches of chemistry that they were all studying kind of independently, and they generated all their own vocabulary. And then as the history of chemistry progressed, what do you know? They're all examples of the same principles. But we keep all of that disparate vocabulary because it's what chemists have used for generations. So your task is just to connect the new vocabulary to the underlying concepts that you already know. Okay, so there's this idea called solubility. And when a chemist says solubility, they mean a couple things. The concentration of a saturated solution, which is the same thing as the concentration of dissolved solute at equilibrium. So if you have a dissolution process, things are dissolving. When do they stop dissolving? Stop dissolving when they come to equilibrium, right? We go back to here. So that process stops moving forward when it comes to equilibrium. How do we know it's come to equilibrium?
Stops dissolving.
When the concentrations are high enough to give you the KSP, right? Okay, that value of the concentration is what we call the solubility. So for sodium fluoride, someone would say the solubility of sodium fluoride is, and I'll make a number up. Suppose it's 6 micromolar. That means I can dissolve 6 micromoles of sodium fluoride in a liter of water. And that's the most I can dissolve. Because that's the equilibrium concentration of sodium ion that you would get dissolved. Okay. So the equilibrium concentration of dissolved solute, that's the solubility. Isn't that also the maximum allowable concentration? Which is, use some new language, also the concentration of a saturated. Saturated solution is one that holds as much of the dissolved stuff as it can, right? Which just means it came to the equilibrium, because you can't go past equilibrium, mostly. Okay, now, up until now, we have done rice tables, and we calculate a concentration at equilibrium in terms of moles per liter, right? So a chemist would call that molar solubility. It happens that often solubility is reported not in moles per liter, but in grams per liter. So when a chemist says solubility, they mean grams per liter. Is it a trick to go from one to the other? You know, moles per liter, you just calculate, convert moles to grams, and then report grams per liter, not so hard. Okay. The thing to keep in mind is that solubility, there's a huge range of solubility. So for example, sodium nitrate has molar solubility is higher than 10 moles per liter. You can actually dissolve 10 moles in a liter of water, which is a huge quantity. What would the KSP value be if the solubility was 10 molar? Greater than 100 KSP value. Okay, so there are also some very small molar solubilities. So sodium bromide, for example, 5.7 times 10 to the minus 7th. In lecture 5, we had a table that we looked at a whole bunch of KSP values, and some of those were like 10 to the minus 40. So there's a huge range in how much stuff can dissolve. Okay. This is not what I thought was coming next. Okay. So can you see questions coming? Well, you just do what you've already done, calculate equilibrium concentrations for a process. You've done that through Rice tables, right? Can we do the same thing for solubility? Yeah. And we predict the amount that we get at equilibrium in either moles per liter or grams per liter. Okay, a couple of terms you need to keep in mind. So a saturated solution. What is a saturated solution? Tell your neighbor what that has to do with equilibrium.
You're there.
It's gonna dissolve.
So a saturated solution is one where the dissolution equilibrium has been reached, which means you can't get any more to dissolve because the dissolving equilibrium, you're already there. Okay. So what do we know about Q and K for a saturated solution? Right, the Q value has reached the KSP value. Okay, an unsaturated solution. An unsaturated solution has not reached the equilibrium yet, right? That can happen two ways. One is that you added a bunch of stuff, you added enough to get to equilibrium, but it's just not done dissolving yet. Is it possible to only add if I pour in some salt into some water, for example, do I guarantee that I can get to equilibrium? I'm seeing some shaking. Is it possible for a dissolution equilibrium to not have added enough starting material to ever get to the high enough concentrations to reach equilibrium? That's usually what we see happening. In that case, we would call it an unsaturated solution. So that means the Q value is less than the K value. Now, in a chemical reaction, the Q value will over time eventually change to finally reach the K value, right? You'll get to equilibrium if you just wait long enough. Is that true for solubility? You have to have added enough for the concentrations to be able to get high enough to reach saturation. So for a solubility process, maybe you didn't add enough to get to equilibrium. And when the stuff stops dissolving, Q still isn't equal to K. And then what happens? You stay there. Everything that you added dissolved, but Q is still not less than K. So you have a solution that it's done dissolving, but you're not at the dissolving equilibrium yet because you didn't add enough material. Okay. Supersaturated solution. Can you have that? Supersaturated solution would be one that was past equilibrium. How can that happen? Josh says, what about temperature? So how you make a supersaturated solution, and you've all done this. How many of you have made a simple sugar syrup for cooking with? So you're like, I have no idea what you're talking about. It's a thing, okay? If you want to dissolve a whole bunch of sugar, it's not ionic solid, but same idea. Dissolve a whole bunch of sugar in water, what do? You heat it up. Why do you heat it up? KSP is higher at higher temperature. So you heat it up, it all dissolves. And then as it cools, what happens? As it cools, the K value goes down. It takes a while for stuff to undissolve. So temporarily you have Q greater than K, and that's a supersaturated solution. Questions that people asked on reading quizzes. Are the rules for solubility equilibrium the same as the one we've already learned? What do you think? Yes, the vocabulary is a little different, and there's a single change in that you might not have added enough for Q to ever get to K. So you have to stop and consider rules. We can use the same equations that we've already learned for KSP, or are there new equations? Are there new equations? The only new equation is that KSP is easier to define than the equilibrium constant. But other than the change in how we define KSP, which we knew that already, it's not different. Okay, is the only change we have to make for the calculations ignoring the solids? Pretty much, yeah, it is. Okay, so there isn't really that much new here, except that you have to now apply everything and think through everything at once to make predictions. Okay, so sodium chloride, table salt, right? You add the water, which is the solid here. It becomes aqueous sodium chloride. How would you do this? What is the maximum concentration of dissolved sodium in pure water at equilibrium? How would you do that? The maximum dissolved solid, maximum concentration of dissolved. What are you calculating here? Concentration, can you just do a rice table for this? Yeah. Another way is to say, what is the maximum possible concentration of sodium ion? You could ask the same question using the words, what is the dissolved molar solubility of sodium chloride? Or what is the concentration of a saturated sodium chloride solution? If you can tell your neighbor why all 4 of these questions would have the same answer. And then we'll go through the calculations.
What is the levels for this? The maximum. That's equilibrium. Yeah.
There could be question number 5 that says, what is the molar solubility of sodium chloride? Okay. If I did a rice table, is this the sweetest rice table you've ever seen? We don't have to include the solid, right? So we don't even worry about it. We start out, nothing's dissolved yet, right? So our initial concentrations are 0. Then some dissolves. The amount we have at equilibrium for a saturated solution is the same as our change line. How do we calculate X? This is the beautiful part. Okay, we know the KSP is 36, right? And we know that the KSP is going to equal the sodium ion concentration times the chloride ion concentration. If we're doing an equilibrium calculation with the rice table, what are these values? They're both X. We get X squared is 36. What's X? 36. Does it get better than that?
No.
No, it doesn't. Okay, so 6, what's our unit for X? So the rice tables are all solved using molar concentrations if we're doing the value, which we are for all the solubilities. Okay, so the solubility is our equilibrium concentration of ions, which is 6 moles per liter. Okay, this is actually molar solubility.
All right, what about the other one that was on the other slide that's in grams?
Okay, so if the molar solubility was 6 moles per liter, how would we convert that to regular solubility in grams per liter? The molar mass of sodium chloride is 18.6. That's not right. What's the molar mass? 32.9897 plus 35.4527 gives you a certain number of grams per mole, right? Take this 6.0 moles per liter, divide it by the molar mass in grams per mole, and you end up in grams per liter. Okay, so this X tells us at equilibrium you get 6 moles per liter, right? So how many moles of sodium chloride dissolved? 6 moles of sodium chloride dissolved per liter. So the molar solubility is 6 moles per liter of sodium chloride. So even though the question about the molar solubility of sodium chloride, they're talking about the solubility of this, that's the same number as the concentration you get because the stoichiometry is 1:1. Josh?
And if it was like, let's say 5 Na and 3 Cl.
Yeah, let's do one of those. Okay, look at this one. Silver sulfate dissolves. Now the stoichiometry isn't 1:1. Okay. So what is the maximum concentration of dissolved silver in pure water at equilibrium? How would you solve that? Do a Rice table, solve for the equilibrium concentration, right? You know how to do that. Maximum possible concentration of silver ion in solution. What is that? That's just the equilibrium concentration. Calculate from the Rice table. What is the dissolved molar solubility? What is the concentration of a saturated silver sulfate solution? Okay. This is an equilibrium problem, right? We do our Rice table, but now when it dissolves, you're going to get twice as much silver ion as you get of the sulfate ion, right? So we have to express that as 2x and x. That slightly complicates our math, still super easy. Our equilibrium expression, we have to square the silver ion concentration. Okay, our silver ion concentration is 2x, our sulfate concentration is x. What's 2x times 2x times x? In your head. 4x cubed, yeah. So we have 4x cubed equals the KSP value, divide the KSP value by 4, take the cube root of that, and you get x. So we just solved for x, which is 4 times 10 to the minus 2 molar. Okay, does x give you this answer? What would you have to do to your x value to get the dissolved ion, silver ion concentration? You have to double it, right? Okay. So you have to double your x value for numbers 1 and 2. How about this one? What is the dissolved molar solubility of silver sulfate? For every 1 mole of sulfate that dissolves, I have to dissolve the 1 mole of starch syrup. So x is also the dissolved molar solubility of silver sulfate. Or what's the concentration of silver sulfate in a saturated solution? X. Okay. Silver chloride is a classic, fairly insoluble, quite insoluble. If you drop a bunch of silver chloride in water, what's going to happen? Some of it's going to dissolve. How much? Teensy bit, right? Okay. So what would the molar concentration of silver ion and chloride ion in water placed in contact with solid? What's the significance of that placed in contact with silver chloride? That means it'll keep on dissolving until it stops dissolving. So it will reach equilibrium. Okay. We start out initially, none of it's dissolved, and some of it dissolves. So our equilibrium concentration is, some of it has dissolved. Our KSP value is going to be equal to the silver ion concentration times the chloride concentration. It's a small number. So we solve for equilibrium concentration X, and we get 10.3 micromolar. Not very soluble. Does that answer the question? Have we answered the question? Yeah, we have. That's all it asks for. Just wants to know what the final concentration is. We solve for it. It was easy. This is the molar solubility of silver chloride. We could report it as solubility, which is Brown's blue. Okay, here's one. Copper 2 hydroxide. What does the 2 mean? If you ever see a metal ion and it has one of those notations in the middle, it's because it's one of the transition metals that can have different kinds of ions. So copper can have copper 2+ or copper 3+. So they're specifying that it's which? Copper 2 plus. You need to know that? Yeah, we do. What's the charge on hydroxide? -1. So you needed to know that it was copper 2 in order to be correct. You have your formula. Okay, copper hydroxide goes to copper 2 plus and 2 hydroxides. We set up our rice table. Where do we go from here? Tell your neighbor what you would do.
Again, for
So you just set it equal to 2x squared times x, which gives us 4x cubed. So take the KSP, divide by 4, take the cube root of it. That's your molar solubility. Is that what the question asked for? So we have to take our molar solubility and do what to it? Convert the moles to grams by dividing by the molar mass. Multiplying by the molar mass, sorry. How do you know to multiply instead of divide, Alex?
Is this the molar mass of the copper hydroxide? Do you do the molar mass of the C?
Good question. Okay, what does the question ask for? The solubility of copper 2 hydroxide. So it wants to know how many grams of the actual copper 2 hydroxide you can dissolve. Okay, this value, 1.7 times 10 to the minus 7 moles of water. That tells you how many moles of copper ion you're going to have per liter, right? Is that the same number as the moles of copper hydroxide that you're going to have? It is because it's a 1-to-1 ratio, right? So we move from the concentration at equilibrium for copper 2 plus, that's going to be the same as the concentration of copper 2 plus. If these stoichiometries were not the same, what then? Then you'd have to correct for the stoichiometry. Okay, because the question is asking for the solubility of the starting material, then you have to do the conversion per gram of starting material. Okay. Here's another one. If you're given the molar solubility, can you calculate people? What does molar solubility mean? So the molar solubility is how many moles of our starting material we can dissolve in a liter, right? But in this case, if we can dissolve 5.71 times 10 to the minus 7 moles per liter of solid, how much are we going to dissolve? How much dissolved? The same number, right? Because it's a 1-to-1 stoichiometric ratio. Okay. So our rice table would look like this, except what do we know? We know what X is. The dissolved molar solubility of solid gives us that many dissolved moles per liter of our ions. So that's what our rice table looks like. Now can we calculate our KSP value? Yeah. You know your concentrations of silver ion and bromide ion at equilibrium. Plug them into your KSP expression and you get your KSP value. It's nice to have the math be a little more straightforward, isn't it? I love that. Okay, take a break. You probably needed one 20 minutes ago. It's okay.
Like, I know.
Definitely did.
No, not.
I'll take it at some. Yeah, I'll have to look at the professors. And,
Okay. Taking it back. When a student asked, do Q and K the exact same way that Q and K do as we previously learned? How would you answer that question? They're exactly the same. There's nothing new Q relates to K, which relates to delta G, as a function of delta G naught, exactly the same way, except we're just looking at a specific kind of reaction with a specific K value, that's a KSP. Okay, one question was, we need to know the solubility rules for these reactions. How many of you remember solubility rules from Chem 105? How many of you remember that you were supposed to have learned them?
I don't know.
I haven't even got that much out of it. It's fairly common in Chem 105 for individual professors to say, here's a bunch of ionic solids, memorize which ones will be soluble and which ones will be insoluble. I don't typically do that. And I don't do that because what does KSP have to do with the solubility rules?
Imagine not.
It supersedes them.
Yeah.
So KSP values reflect the maximum concentration of ionic salt, right? Things that have a high KSP value, are they soluble? Yes. Things that have a low KSP value, are they soluble?
Yes, but no.
Yes, but no, right? So the solubility rules, soluble, usually the things that you had to call soluble in Chem 105 would be the maximum concentration is 0.01 moles per liter and higher, which you can get from a KSP value, right? Things that we call insoluble just have a low KSP value. Well, like 10 to the minus fifth, probably. So is there really two baskets, soluble and insoluble? There's less soluble and more soluble, which is defined by the KSP, right? Okay, so compare this. How are Q and K connected? We kind of did this already, so we're just gonna. Let's talk about adding sodium chloride. So pretend you have your glass. You decide you like to drink salty water. So you take a scoop of salt in your spoon and you pour it in your lots of water. Okay. In non-chemistry terms, as you stir it, what's going to happen? It's going to dissolve. Probably, how much of it will dissolve? All of it. Sodium chloride is pretty dang soluble. Has a high KSP value. KSP is 36. So if you just add a spoonful to water, it will dissolve. Okay. As soon as you add it in, now think of that process in terms of what we've been doing in this class. What are our initial concentrations of sodium ion and chloride ion the moment you add it? 0, right? And then as it begins to dissolve, what happens to the sodium ion concentration and the chloride ion concentration? Increases as it dissolves, right? Okay. So before any of the sodium chloride has dissolved, what would our race table look like? What would our initial line look like? 0, 0. Okay. So the reaction is a solid sodium chloride dissociates to form sodium ion and chloride ion, and it's governed by the KSP value and expression. Okay. What is Q at the moment that you add your sodium chloride? It's 0. How come? At time equals 0, did you have a chance to dissolve anything yet? No, so Q is 0. Okay. What's going to happen to Q when you stir it? Say it out loud, Ben.
It increases in purchase K.
Okay, as you dissolve more of the salt, your sodium and chloride ion concentration will go up. The Q value is calculated the same way as the KSP, except the concentrations are those you have at that moment in time, not at equilibrium. So as your concentrations of dissolved ion goes up, what happens to Q? It goes up. Yeah. Okay, here's the question. When does Q stop going up? There's actually two possibilities here. One is, depending on how much salt you've added, Q stops going up when the concentration of dissolved ions is high enough that Q equals the KSP, right? You have a saturated solution. What's an easy way to recognize a saturated solution? Often a saturated solution has some solid floating on the bottom that couldn't dissolve because it reached saturation before everything dissolved. If you see a solution that still has solid floating on the bottom and you stirred it and waited and stirred it and waited, what do you know? It's a saturated solution, Q equals the K3. Okay, when is the other time that dissolution could stop? So imagine you just added your like teaspoon of salt to your glass and you're stirring it around. What could happen? Chances are all of it will dissolve, right? So then dissolving stops when you've dissolved all the solid that you added. Does that necessarily mean you're at a saturated solution? No. Okay, if what you've added, all of it dissolves, calculate the concentrations when all of it's dissolved. You can calculate Q, right? Is it possible for the dissolving to stop when Q is still less than K? It is. If K is really high and you didn't add very much material, you might run out of solid before you get to saturation. Okay, so does Q always reach K for a solubility process? Often it doesn't. Often, you take however many moles that you added, and all of it dissolved. And when you calculate the moles per liter for all of it dissolving, you don't have enough to get to a saturated solution. So then you're done. Unsaturated solution. Okay, here's a question for you. Many of you played the game on the quiz where you answered and it was wrong, and then you said, well, let me try another one. Still didn't really understand what was going on, right? Okay, I'm not criticizing you for that. Let's revisit it. What is precipitating? So if dissolution or dissolving is the solid going into solution, that's what happens when Q is less than K, delta G is negative, and the reaction moves forward. What's it called when the reaction moves backwards? That's precipitation. Okay, so when this process is moving left to right, that's dissolution. When the reaction is moving backwards, what you're doing is the dissolved ions are becoming solid. That's precipitation. Okay, so when does precipitation happen?
I watched a video yesterday of, he had two separate beakers of different ions and he poured it together and it was creating like this yellow solid. It's really cool.
Common ion effect, we'll talk about that in a minute. Okay, so what do you know just from before about when does a reaction move backwards? Delta G is positive, which happens when Q is greater than K. So in this case, things precipitate when Q is greater than the KSP. That's complicated as it gets? Actually, yes, it is. Okay, so which one is less? Let's evaluate this. If the reaction quotient is less than the KSP, so delta G negative, so which way will the reaction go? Forward. So is this going to be precipitation? No. The reaction quotient is greater than the KSP value. Then the reaction has to move backwards. So yeah, that's precipitation. Evaluate these ones. The change in free energy is positive for the precipitation reaction. It's positive for the precipitation reaction. What's it negative for? Dissolving. So is that the right answer? Okay, the change in free energy is negative for the dissolution reaction. Which way would that reaction be moving? Forward. So the only one that results in the reaction moving backwards is B. Precipitation is just a solubility process moving backwards. Okay, does that assume that when we talk about solubility, we always, always, always put the solid on the right? Yes, we always do this process where we put the solid on the right. I'm used to, yeah. Facing here and facing here are two different things. So you know that when I draw, you know, which way is the reaction going, I have to flip everything when I stand in front of you. It works until I turn around and face the same way you do, and then I flip it twice, and that doesn't work so well. Okay, so always draw the solubility reaction with the sodium chloride on your left and the dissolved ions on your right. So it has to be in that direction. Okay, spend a few minutes working on recitation. Right here. Okay. So take this back to magnesium chloride. Question is, if you try to dissolve magnesium chloride in seawater, get more of it to dissolve than in fresh water or less? Okay, people are saying less. Tell your neighbor why you know from the equations that you would get less magnesium chloride to dissolve in seawater than in fresh water.
You're right. That's gonna shift back towards polymer. Right here. Agree. Couldn't have said it any better.
It's bigger than the K.
So will the KSP value change between the seawater and the freshwater? No, not unless you're changing the temperature. So the KSP value will stay the same. What changes?
You,
The initial Q value that you start with. So which one will have a higher Q value for dissolving magnesium chloride? The seawater or the freshwater? Seawater will, because your total chloride concentration will be higher in seawater. Because the seawater has sodium chloride in it already, so it has a chloride ion concentration. Okay, so when you dissolve magnesium chloride in seawater, the Q value you start with is higher than the Q value for freshwater. So what does that mean for the delta G values? Remember, delta G comes from the difference between Q and K, right? If we make Q bigger in the seawater because of the existence of the extra chloride ion, what happens to the difference between Q and K for seawater?
Smaller.
It gets smaller. So what happens to delta G? Gets less negative. So when the reaction moves forward, how far does it move before it gets to delta G equals 0? Not as far. So you don't dissolve as much because the reaction doesn't move forward as far. Okay. Think about it in another way. If we have a saturated solution of sodium chloride, what do we know about a saturated solution of sodium chloride? Delta G is 0. It's at its maximum concentration of sodium and chloride. What do we know about the Q value?
okay.
It's equal to the KSP. So the Q value is 36, right? When it's at equilibrium. Okay, calcium chloride is even more soluble than sodium chloride. So if I take a little bit of calcium chloride and I sprinkle it into my thick saturated solution of sodium chloride, some of that calcium chloride is going to dissolve. When it does, what's going to happen to my chloride concentration? It's going to increase. Okay, when the chloride concentration increases, what's going to happen to the Q value for sodium chloride? It's also going to increase because the Q value includes the chloride. So then what do we know? We were at Q equals the KSP. Now we increase the Q because we added a common ion. So what do we know about the sodium chloride equilibrium? We know that the Q value for sodium chloride is now higher than the KSP value. We now have a supersaturated solution because of adding the calcium chloride to the common ion effect. So what's going to happen to the sodium chloride? It's going to shift backwards. So the sodium chloride, some of the sodium chloride is going to precipitate. Yeah. Here's a reading quiz question. You're trying to dissolve the maximum amount of sodium chloride. Which process is likely to work the most poorly? Dissolving sodium chloride in pure water. Dissolve sodium chloride in 1 molar potassium chloride. What's going to happen? We have 1 molar chloride in there as a common ion. So we're trying to get the sodium chloride to dissolve when there's already 1 molar of one of the products. So what did we just do according to Le Chatelier's principle? stomped on the product side, right? So will the reaction move forward as far? No. Okay, now compare it to the sodium, the dissolving sodium chloride in 1 molar magnesium chloride. What's the difference between 1 molar potassium chloride and 1 molar magnesium chloride?
Chloride.
The chloride concentration in 1 molar magnesium chloride solution is actually 2 molar chloride, right? Okay, so what's harder to do, B or C?
See,
B. Now compare A to B to C. What works the best? A, then C. Okay, evaluate this choice. Is the solubility of sodium chloride defined solely by its KSP? You have to include Q and the KSP to get a feeling about what's going to happen, right? And the common ion effect messes with Q, changes your value for delta G, which changes how far the reaction shifts forward, which changes how much material will dissolve. Lots of connections there. Okay. What I want to do, I want to quick show you a couple things. And then I want you to work on recitation and the post-lecture quiz. This is my very favorite post-lecture quiz of all time. What does that probably mean for you? What it means is it's designed to identify all of the wrong thinking that can lead you to the wrong answer. It doesn't mean it's too hard, but it means that you do want to be in a situation where you can get feedback to identify the wrong thinking, so then you can do the right thing. Okay, here's a question somebody asked. Does the common ion effect only apply to dissolving ionic compounds? What do you think? We introduce the common ion effect when we're talking about solubility. But any reaction where you have more than one equilibrium going on in the same solution, if they share one of the products, they're going to act this way. Yeah. And we do it in unit 3. Okay, here's a question. Common, Ben.
Common ion effects, does it have to be the same? It's on the right and stable, they have the
Okay,
same
So
charge.
Ben's question is the common ion, does it have to be the actual identical ion? Or can we say lithium and sodium act kind of the same, so it actually has to be the same ion. So it has to be something that shows up in the equilibrium expression for both solutes, and it has to be identical. That makes it easier, right? Josh,
I can ask it later. I was wondering, so like if you do have lithium and let's say sodium, and then you have one with a lower solubility, like a lower solubility compound, but then it's in solution, will it pull?
it can, and I'll show you one. If I'm understanding your question, I think you would get it. Okay. So when do things dissolve? When Q is less than K. When do they precipitate? Q is greater than K. Would that allow you to look at any solution and know whether things will dissolve or precipitate? Yeah, it does. This actually comes up in real life, believe it or not. So my husband is a chemist like me. Gotta pity our children, right? Actually, I have a brother who is a chemistry professor as well, and my dad was a high school chemistry teacher, so a little too much of that going on in our family. Okay, so because my husband is a chemist, he's not afraid of making solutions, which means that we have this great hydroponic garden on our back porch. Josh has seen it. I don't think, have you seen it this summer?
Yes, yeah, with the tomatoes.
So a hydroponic garden doesn't use dirt. You have a solution of nutrients that pumps into the roots and pours over the roots every 10 minutes or 15 minutes, or it just sits in a solution of nutrients. So you have to make up the big barrel of nutrients that the plants are going to drink. And it has, you know, a whole bunch of different chemicals that you put in it that are things that the plant is going to need. Well, my husband discovered that you have to mix the things in the right order Because there's one particular thing that you have to add to the end when everything is diluted to almost its final volume, or else you cause a precipitation reaction. How come? If you add it too early, when the total volume is low, concentrations are high enough that Q is greater than K, you cause a precipitation. If you add it last in the process, then the total volumes are bigger, which keeps your total concentrations lower, and Q never gets to K, and so everything stays in blue. Okay. So if Q is less than the KSP value, tell your neighbor what's going to happen. What does that look like?
Delta G is
Okay, if Q is greater than KSP, what's going to happen? Now it's a supersaturated solution. How does the equilibrium respond to supersaturation? It shifts towards starting material, so you see precipitations. You can always predict whether an ionic solid is going to dissolve or not by figuring out, or if all of it is going to dissolve, by calculating what Q would be and comparing it to KSP. You can do that in the presence of a common ion, or just all on its own. What do you think the post-lecture quiz is going to ask you to do? Predict, yeah. Okay, so here's an example. You have a liter of solution that has 10 millimolar sodium sulfate in it. And you want to add, for some reason or another, you want to add 50 milliliters of a solution of calcium chloride. Now, what we've done is we have two different cations and two different anions, right? So there are three different combinations of cations and anions, each of which is going to have its own KSP value, right? Okay. If something is going to precipitate, which one is it?
Calcium sulfate.
Okay, Josh, why the calcium sulfate? How do you know?
Fluidly soluble.
It has the lowest KSP value. And I'm recording and I'm not actually wearing my microphone. So that's not very helpful. Okay. If something is going to precipitate, it's going to be the one that has the lowest KSP value because it's the least soluble. So in these three combinations, how soluble are calcium chloride and sodium sulfate? Way soluble, right? So we're not too worried about them precipitating because we don't have super high concentrations. But is it possible that calcium sulfate could be precipitating? Now notice, did we actually add any calcium sulfate to our solution? We didn't. But do we have calcium sulfate in our solution? Yes, because all the ions are floating around, so all the possible combinations are available, right? Okay. So we need to construct a Rice table for the calcium sulfate to figure out what we have, to figure out if it's all going to dissolve or if it's not possible to dissolve all of it. The problem is that we started with a liter and we added 50 milliliters to that. So we've diluted everything. So if we first have to recalculate all of our concentrations considering the dilution. So our calcium concentration, when we add everything. We started with 50 milliliters, right? We started with 0.001 molar calcium from our calcium chloride. But we're going to change its volume from 50 milliliters to a liter and 50 milliliters because we're putting it into the larger solution. When we calculate that, after the dilution, we have certain concentration. As a sulfate concentration, we know what we started with, right? We started with 0.01 molar sodium sulfate, but that also gets diluted from a liter to a liter and 50 milliliters. Okay. When we do there's two ways to process this. Can we simply calculate a Q value for calcium sulfate using those concentrations in our initial line? We can. And when we do that, if the Q value is greater than the KSP value, what do we know? some of that is going to precipitate, right? The other thing we can do is solve for R. Who wanted a different approach? You solve for X. Compare that value to the value that you get in the presence of water. It's easier to just do the KSP or do the Q value, right? Okay. Calculate our Q value. What does our Q value tell us here? KSP. Are we a supersaturated solution here? Q value is less than the KSP, right? So what does that tell us? It will all stay dissolved. So the calcium sulfate will all stay dissolved in solution. Are we going to cause a precipitate? No, we're not. No precipitation. Last week we talked about metal chelation and the formation of complex ions, and I showed you all of these really huge equilibrium constants, formation constants. Where's the equilibrium lie? Far to the right. Okay. So let's look at silver cyanide. Down here. Tell me about this reaction. Equilibrium lie. Crazy to the right. Okay. Here's a question for you. So silver chloride is not very soluble. If you add cyanide ion to it, like suppose you add sodium cyanide to it, the silver chloride solubility goes up a lot.
Being converted to silver cyanide.
We have two reactions, right? That could happen. So we have silver chloride that we add to the water, but the water also has cyanide in it. So when silver ion forms in solution, what is that silver ion going to do? It's going to react with the cyanide. We'll pull it out of solution. So what does that make this reaction do? It keeps on going because Q doesn't go up when the silver chloride dissolves, because as soon as the silver ion forms, what happens to it? It's removed from solution and becomes silver cyanide instead. Is this an example of the common ion effect, sort of? Except that it's kind of the common ion effect in reverse. It's an example of the Chatellier's principle. When you remove product as it forms, what happens? The reaction keeps going forward, and that applies to solubility reactions as well. Okay, here's a question. Remember when we talked about linked reactions and how you could calculate the K value for a linked reaction by multiplying the individual K values? If we take these two K values for the linked reaction, and we multiply them for a net reaction, the resulting K value, where's the equilibrium line? Right. So by linking something that's mostly insoluble, removing one of the products as it forms by linking it to another reaction, what happens to the solid silver chloride here? It appears to dissolve because it's disappearing, right? But we're trapping it in a different way. This is sort of an example of the Chatellier's principle. Okay, you have all these equations. Allie pointed out that when your recitation printed, it didn't have the half equation. So you have that. There is a recitation, not recitation, there's an equation sheet under content that looks more like what's on the exam. All right, so work on recitation in the post-lecture quiz. Apply these ideas.